thank you everyone for attending this. So this is the soft matter seminar series that we have started since last month. So we have our speaker, Dr. Shen, with here. But before that, I'll just go over a brief overview of the program. So just the overall, these. So what we will do is Dr. Sen will go over his presentation, and at the end of it, we will open it up for discussion. And again, this is a very casual conversation type thing. So if you have a question, either raise your hands up at the end of his talk, or just you can just speak out. One quick suggestion is like if you are not talking, it will be really helpful to mute your mic. Otherwise, it can sometimes become a little distracting. So let me share my screen. So can everybody see my screen?
I can.
Okay, awesome. So we are going to listen to Dr. Sen's talk about active matter swarms for cargo capture, transport, and delivery. And just just a so the agenda is there will be a little brief introduction to BPS and soft matter complex fluids program. Then we'll go into the presentation, and finally we'll reflect and discuss. So who are we? So my name is Suman Sinha Ray. I'm the lead discipline scientist for soft matter. So we are based out of NASA Glenn Research Center, which is part of BPS, Biology and Physical Sciences at SMD. So here we are responsible for the soft matter research, which can be broadly classified into two categories: active media and granular media. And under active media, colloidal science and non-Newtonian fluids and rheology falls. So our mandate is to promote fundamental science in micro or reduced gravity, like lunar, Martian, that can also capture taxpayers' interest and imagination and progress the fundamental science. So here are some of the microgravity research listing I have. I will put these links in the chat for your if you want to go through them. There are some QR codes. You can scan them. If you are interested, please feel free to email me. You have my email ID. I'll not go through all of this right now because you can take a look at them at your own convenience. So why are we here? So we are doing this because this is a follow-on based on the 3 mini workshop that we organized last year, where across US there were 60 plus soft matter researchers who have participated. And what we found out that in during that during that conversation, and the researchers came back to us and they said like they really like this forum. They think that we should keep on doing this so that we can keep the soft matter community engaged and create a knowledge exchange platform and generate awareness. And I would like to mention that within the next few months, the decadal survey is going to come out, and we want to make sure that the community remains crystallized so that uh, when the directions for soft matter research comes out, we can easily mobilize across it. So if you are interested in giving a talk, please email me, which is suman.sinhare@nasa.gov, or there is a form which is here, and the QR code is here. If you feel like you can scan it, I'm going to drop this link in the chat. So please feel free to fill out this form, and you can always email me. So two announcements that I have. So we are looking for postdocs and interns in the field of soft matter. So especially in the field of active matter. So if you have an interest candidate, we would love to know. Please ask them to send their resume to me. I would love to talk with them and know more about them. We hire interns on a regular basis, and these are undergrads. So if you're undergrad or graduate students who want to come for internship for a semester onto the campus, would love to know. The next seminar is on April 27th, which will be provided by Dr. Simon Rogers on a generalized memory function based recoverable strain and its relation to nanoscale structure. I will send out the invitation right after this talk ends, and I would strongly suggest Simon is a great speaker on the field of rheology, and it will be of real importance, I think. So, without much further ado, our speaker today is Dr. Ayushman Sen, who is the Varnu Willeman Professor of Chemistry and Distinguished Professor of Chemistry and Chemical Engineering at Penn State. He is a fellow of both American Association for Advancement of Science and the Royal Society of Chemistry. He is the recipient of Alexander von Humboldt Prize, and he has a medal from the Chemical Research Society. His research interests encompass active autonomous systems, synthetic nano and micromotors, micropumps, and systems chemistry. He is the author of over 400 scientific publications and holds 25 patents. And his pastime actually looks into enological and gastronomical exploration. So, on my side personally, I would say when I was a PhD student, I eagerly read his scientific publications. He has been a great inspiration to me personally. So I would uh, I was looking forward to this talk, and I think you will too. And so, Dr. Sen, I would like to hand it over to you.
Thank you, Simon, for the very kind introduction. Let me share screen then. Okay, screen, entire screen. Share. Okay. Can you see it?
Yes.
Okay. All right. So, as Shuman said, we want to talk about one aspect of our work today, which involves particles, titanium dioxide particles. And this is a collaboration between our group, who do the experiments, and Anna Balazs's group at the University of Pittsburgh, who has done the modeling. I won't talk much about the modeling. I will just focus on our experimental work. Funding is through the Department of Chemistry. But before I get into it, let me just talk briefly about why gravity matters in active systems. So the active systems are defined as systems that are out of equilibrium, and they're driven out of equilibrium by a constant input of energy. So these systems, and I'll show you examples, show motility, they show collective behavior, interactions with each other, and so on. And so they have become quite in vogue, shall we say, in research. And why does gravity matter in this area? Well, first of all, if you're dealing with particles, they have a tendency to sediment if they're heavier than the liquid in which they are, or float if they're lighter, and that can affect their behavior. Um, these particles can generate convective fluid flow. And so that, of course, depends on the buoyancy effects, which is obviously gravity driven. And of course, they also can undergo gravitaxis, which is reorientation in gravitational field. So these three features introduce some complexity into the research on active matter, and it would be nice to try to deconvolute the effect of gravity from the other factors that drive active matter. So the opportunities that zero or microgravity conditions allows are, for example, we can probe propulsion mechanisms because we can rule out the effect of gravity. So for example, if the propulsion mechanism of these active matter systems involve, let's say, buoyancy driven flow, diffusive phoretic motion, and so on, we can separate these from one another by turning on or turning off gravity, if you will. So that's an example. Also interaction and 3D assembly of matter under non-equilibrium conditions. And again, in terms of assembly, if these particles tend to settle under gravity, then the assembly would be different from what you would if gravity was absent. There are other issues like rheology of soft matter, surface-driven soft adaptable materials that also require us to rule out gravity in many of the mechanisms. So what I'm going to focus mainly are the first 2 points here and show how we can combine mechanisms that involve gravity and other mechanisms that do not involve gravity and do interesting things. And again, as I said, if you turn one of them off, then it's much easier and makes the study of these systems much simpler. So what are we trying to do? So the grand challenge is to design synthetic active matter that show emergent properties and complex functions based on interactions between themselves, interactions with the environment, and so on. And so these are systems that are driven from equilibrium by constant energy input. Now, to make these systems, you need two things. You need a source of information, code, and typically in our systems that this involves chemical gradient or light gradient, and you need something that can decode and process the information. And in our case, these are motile particles. I'll get back to these videos later on, but let me just say that all the videos that I will be showing you are all real-time videos. They're not speeded up, slowed down, etc. So an example that we're all familiar with is, of course, that if you're hungry, since this is lunchtime on the East Coast, maybe we want to get some French fries, and so we start walking towards the source of French fries. We don't need to actually see the golden arches. We can just follow the odor trail. And so that's an example where the information is in the form of a chemical gradient, and we are the self-powered object. And so the interaction between these two would lead to collective and emergent behavior. So why are we interested in these? Well, rationally designed dynamic materials that can remodel themselves and transform the environment can optimize performance. Typically now, we design materials for a single performance, but these materials, the active materials in principle, can adapt and carry out different performances by evolving their structures. They can, since they can communicate with each other, they can accomplish tasks collectively and emergently. And since they're self-powered, they're not tethered to any power source. They can move around. You can have mobile sensors and so on. So there are a lot of different reasons why these are interesting materials. Now, what I want to talk today is about transportation of large payloads by active systems. And if you want to transport large payloads, a single active particle doesn't generate enough force. You need them to act collectively to transport these large payloads. So it's the analogy in the insect world, for example, are the ants, where a single ant may not be able to carry a large piece of food, a cockroach, for example, but a swarm of ants can do that. And so that's what we are trying to design. So before I show you actual examples, let me discuss some of the mechanisms that we use. So one of our mechanism involves is actually um, based on the idea of quorum sensing. And so the quorum sensing, uh, for example, if we get infected by a few bacteria, we don't fall sick immediately. It takes an incubation period of 7 to 10 days before we start to feel the ill effects. And the question is, what happens in those 7 to 10 days? Well, the bacteria multiply. And when there are enough of them, then they launch the attack. Now, the question is, how do they know that there are enough of them? And the way they do it is by secreting a quorum sensing chemical, and each bacteria will then monitor that chemical. And when it reaches a certain threshold level, they know there are enough of them. So in our case, we'll have particles that secrete ions. And these ions can diffuse. And let's say that the cation, being smaller, diffuses faster than the anion. That will create an electric field, and the particles will then respond to the electric field by moving. And furthermore, if there are enough particles, then these ion gradients overlap, and then they start to interact with each other. So this is just an equation which shows that the speed of motion depends on the gradient, ion gradient. The difference in diffusivity between the cation and the anion. And of course, if the sign changes, then the motion is in a different opposite direction. And the difference in the charge on the particle, the zeta potential in the particle versus the wall, if it's near the wall. And this is the dominant term. There is a chemiphoretic term. Now you notice that there is no mass in this, and this is because we're in low Reynolds number, and mass is not important. The speed is basically proportional to the ion gradient and the charge on the particle. So for example, taking a very simple example, if you take silver chloride, which is a basis of black and white photography, you shine light on it, you get a decomposition to make silver atoms, but you also make protons and chloride ions, and protons, being smaller, diffuses faster than the chloride ion. So you have an electric field pointing inwards to which the particle can interact and move. You also have an electroosmotic flow. If you're sitting on a glass surface, then the double layer is positively charged, so the electroosmotic flow moves things inward. And so you can cause motion and collection in this way. So here are some silver chloride particles. The light comes on, they start to move, which is interesting. But what is more interesting is that they start to form little colonies over time. And the bottom three panels are the model for slime mold, which is a quorum sensing organism. And we can use the exact same model as slime molds to model these systems. So the bottom line is that they're beginning to show some collective behavior that mimics, not the exact mechanism, obviously, but they mimic what living systems do. Now you can play games with these things. You can have two sets of particles, one of which secretes ions, but all particles will respond to those ions. And so you can have a prey, which is the particle that secretes the ions, and a predator, which may be an inactive particle which responds to the charge gradient. And so here the black ones are silver chloride particles. The light colored ones are silica particles. And as you can see, when the light comes on, these move, but the silica particle senses the ion gradients and surrounds them. So it's like a wolf pack, if you will, surrounding the silver chloride particles. Why this is important is because it shows that you can move two or more different particle types without attaching one to the other. You can have coordinated movement. And if you're trying to make a smart system of particles, you don't have to put all the functionalities on the same particle. You can have one set of particles that do one function, and then they can send a signal to a second set of particles, which can then carry out a second function. So it makes life easier making nanorobotic systems. So these are attractive interactions. I'll show you a video of a repulsive interaction, and I'll just call it a shark chasing a school of fish. It's kind of obvious. And so we can tune these interactions to be repulsive or attractive if we want. Now, the other thing is that these silver salts, silver chloride, silver phosphate, when you shine light, you make silver and you make ions. Now, if you also add an oxidant, and an example of an oxidant is hydrogen peroxide, what happens is the reaction is reversed in a sense, and you get back to the silver salt. And sorry, something happened here. And so whatever the ion gradients were in the presence of light, when the oxidant reoxidizes, the ion gradients are reversed. Okay. And so you have ion gradients one way during the reduction step, which is light induced, and in the opposite direction during the oxidation step. And this leads to oscillatory behavior. So you can see these here, where this collection of silver phosphate particles start to show these oscillatory behaviors. And it's actually kind of interesting because you can use these oscillations for annealing. So what I mean by this is if you want to make colloidal crystals, for example, one way you can anneal them is, of course, by heating them. But you can also anneal them by putting just a few active particles, which basically shakes up the system and over time causes the crystallization to be more and more defect free. So for example, you can barely see the silver salt particles. The larger particles that you are seeing are silica particles. And as you can see, because of these oscillations, they start to slowly anneal and make more defect-free structures. Now, the other thing I want to point out is that these have some possible utility. For example, bone is hydroxyapatite. And if you scratch a bone or you have a hairline fracture, you have leaching of calcium ions and phosphate ions and hydroxide ion, of which the hydroxide ion is the fastest diffusing. So you have an electric field pointing outward, which means if you have negatively charged particles, they will move into the crack. And so here is an example where you have a hairline fracture on a bone, and using quantum dots, which are negatively charged, they move in and they light up the crack. We have also shown that you can use polymeric particles with bone growth factors, which will then migrate preferentially to the crack and start to regenerate the bone. So these are examples of ion gradient induced motion, diffusiophoretic motion of particles. Now let me move to another mechanism, and this involves also light, but this involves a convective flow, which is buoyancy driven. So if you have, let's say you shine light, and that causes a local heating, then you have a convective flow upward and then round from the sides. And if you have particles, they will collect in the middle. And if you move the light source, they will move with the light source, and I'll show you that. And you can actually transport particles this way. And so in what I want to talk about mostly is this system where we use three different mechanisms. One is this photothermal convection, where, as I said, you do light-driven thermal heating, which sets up a convective flow. And this causes particles to collect at the center of the light. If you use titanium dioxide particles, they secrete protons and hydroxide ions. And because protons diffuse faster, you again get a diffusive osmotic flow, which brings the particles together. So these two causes an aggregation of particles. The third one is the photocatalytic generation of oxygen by titanium dioxide. And this happens where the density of the particle is highest, and then the oxygen moves out. So you have a non-electrolyte diffusivephoresis, which causes the particles to separate. So two mechanisms that causes particles to aggregate, and a third mechanism which causes the particles to separate. And these two are light induced. This one is not. And the setup is very simple. You have a hybridization chamber, if you will, and we put a solution of the suspension of the particles in it. We cover it up, and we can look at through microscope, and we can shine light on them, and then they look at what's happening. First, the fact that you can, so this causes aggregation, this causes separation. So if you shine light, what happens is you start to see these oscillations of the particles. And so this is the ratio of the expanded size to the original size. And you can see it goes up and down, depending on when you turn the UV on and off. And it depends also on the light intensity. Higher the light intensity, more is the expansion, because you're making more oxygen, which is pushing the particles apart by non-electrolyte diffusivephoresis. And you can monitor the oxygen formation too. Then the photothermal effect, which is, for example, if you shine light here, there's a local heating. So there's an upward movement of fluid, which brings all the particles to this point. And so you can see these particles moving to this point here. You don't need much of a difference in temperature. A local heating of a few degrees Kelvin is more than enough for this phenomena to take place. And interestingly, you can move very large swarms this way. So this is a swarm of titanium dioxide, and we move the light source to different regions, hundreds of microns apart. So here is a swarm, the light spot is here, and it moves towards that. And then I move the light spot here, so it moves there, and then up here, and so on. So so these swarms of particles will move to where the light is, and the speed is quite fast. And this gives you some idea of the speed. We're talking about several microns per second. And of course, the speed of motion depends on the light intensity. And so as you increase the light intensity, the speed will go up. And this video shows that, but I don't want to dwell on it too much. You can bring swarms together to a particular light spot. So here is a swarm of titanium dioxide, 4 of these actually, and over time they come to where the light is being directed, and they merge and form a large swarm. And I've shown you the motion of titanium dioxide swarms, but you can incorporate other particles in them. You can put in inactive polystyrene particles, you can put droplets in them, you can put micelles in them, and they all get incorporated into these swarms. Um, and the other interesting thing is that when you turn the light on, as I showed you before, these swarms will come together. But one of the interesting things is the passive particles are expelled and they collect around the swarm. And so you can see that all the passive particles that were in the swarms, when the swarms collect, they get expelled and they surround the titanium dioxide um, particles. Okay. Um, so again, these are the three mechanisms. The light-induced motion involves either an inward motion because of thermal heating, or an outward motion because of the generation of oxygen. Um, when you first hit it with light, this dominates the outward flow because of non-electrolyte diffusivephoresis, but over time, the photothermal convection starts to dominate over this. And then you have the aggregation due to the electrolyte diffusivephoresis, the secretion of protons and hydroxide ions. And so this, so let me go back to this a little bit and dive into it a little bit more. So as you can see, at the wall, of course, there's no slip boundary condition. So there's no movement. And so as you go up from the wall, the fluid flow will increase. And then halfway through the chamber, because of fluid continuity, the flow will have to reverse. And so it's inward here, but as you go up, it reverses. And so what you end up is an S-shaped curve. So if you plot the velocity versus the height of the chamber, what you get is this S-shaped curve. So at the bottom, no slip boundary condition, the velocity is 0. Then it increases. And then as you get to the center, it decreases, and then it reverses back. And you can see it in the stop video here, where we slowly go up and we look at the particle motion. So as you see, as you go up, the particle speeds up and it's going from right to left. Then the slow down as we approach the halfway point, and then the reverse. And then the speed up again as we go higher and higher. And so you have this beautiful S-shaped curve. The other interesting point, which has to do with this no slip boundary condition, is that the velocity increases as you move away from the wall. And so if you have a collection of particles, some of which are large and some of which are small, what would happen is that the larger particles will see the greater flow because they're sticking out into the fluid. The smaller particles are closer to the wall where the flow velocity is 0 because of no slip boundary condition. And so the larger particles move faster than the slower particles. And you can see this plot here where I've plotted the diameter of the particle versus the velocity. And the velocities are quite high, 15 microns per second here, for example. And as you go to smaller and smaller particles, the velocity drops. And you can see this in this video where we have a collection of large particles, very large particles, intermediate sized particles, and small particles. And as I turn it on, you can see that the large particles move much faster than the smaller particles. And so what this allows is to have cargo particles, passive particles, being sorted out by size and released according to their size. And okay, something happened here. It's trying to save or doing something. I don't know what the hell. Sorry, give me a minute here. Maybe restart the program. Okay. You can still see it, right?
Yes.
Okay, good. Sorry about that. So we can separate particles, as I showed. The particles that separate out from the titanium dioxide swarms, which are the carriers. You can move them from one side to the other side. You can release them, taking advantage of the difference in sizes in the flow. You can go back and pick some up and then release them again, and so on. So you can keep doing this. So here is an all-encompassing video, if you will. So you can see these large polystyrene particles being moved from one side of the swarm to the other and being separated out. You can see them being released because they're big particles. They move faster. So the big particles are released before the small particles, which are these little particles here. And then at the end, the smaller particles start to get released. And so you can sort them out and release them according to the size. It's not perfect, but you can see what I mean. And then, of course, you can go back and let's see, go back and pick up more particles and then move them again and release it. So you can go back and forth, pick up particles, release them, pick up particles, release them, and so on. So I think what I've shown you is that these titanium dioxide swarms can undergo directed long-range migration. We don't need any chemical fuel. It's all self-generated. They can perform collective functions. They can carry large loads of cargo particles, big polystyrene particles, for example, and you can repeatedly isolate and deliver specific components of multi-particle cargo. And the other nice thing is this is all controlled by light, which means that you can apply it remotely, you can pattern it with a photomask, and you can move things by irradiating specific locations. I've been pushing this idea of systems materials, which is the study of interactions and feedback between individual units of an active system and how it can give rise to function and performance of the entire system. And of course, scaling matters. How do you go from motion at the molecular level to microscale? And we have examples of these, but I won't talk about them today. And so some of the things that we need to address is, can you fabricate these systems based on modular structures of discrete autonomous units? And I showed you, I think, that you can using individual titanium particles, and you can have them come together and reorganize themselves. So they can collectively assemble themselves through interactions, diffusive-phoretic interactions, and you can program them using light. The fourth point is an interesting one, which has to do with information, and this is something we are still wrestling with. How do we impart information into these active systems so that they can communicate and do interesting things? So systems materials, I draw the analogy from systems biology, which is cells to tissues to organisms. And Philip Ball has an interesting article in this area in one of the more recent MRS bulletin. So I will stop here. This is kind of our dream moving things. This is actually taken from Audi magazine, which is Audi makes cars. I don't know they make nano submarines, but this is nano submarines moving through capillary. This is sort of the same idea as Fantastic Voyage and fixing things in the body. Of course, we are very far away from this. Um, we are kind of like here, where this was the first computer mice back in 1968. And so maybe in another 50 years, computer mice has come a long way from this. And so maybe in 50 years, maybe we'll get to this. One of the reasons we have gotten interested in swarms is in the context of drug delivery. If you want active drug delivery has many advantages. You don't need a large dosage because you can direct it to the specific disease spot. Um, it's faster because of the active motion. But if you want to provide an adequate dosage, often one active particle may not be able to carry all the drug that you need. And so you would need swarms. And then you need to understand how to manipulate swarms to do what you want to do. So I'll stop here, and I'll stop here and be happy to take questions.
Thank you, Dr. Sen. Thanks a lot for the presentation. So any question from the audience? If you have a question, just you can speak up.
Maybe I can ask a question. This is Bhuvnesh Party. Great talk, Ayushman, like always. I have a question
You're very kind. Yeah.
about these predator prey systems that you have studied in the past.
Yeah.
Have you ever tried to quantify the degree of non-reciprocity in these interactions?
I was actually hoping that someone would bring up this non-reciprocity issue. So for everyone, one of the signatures of active materials is this non-reciprocal behavior, the predator-prey behavior, which is an apparent violation of Newton's third law, which is all the forces are reciprocal there. And there's been a lot of excitement about this non-reciprocal behavior. So Bhuvnesh, we're about to submit a theory paper on non-reciprocal behavior at the molecular level, and where we show that without any ad hoc forces, you can generate non-reciprocal behavior in catalytic molecules, enzymes to be specific. So yes, we're trying to attack it from both experimental point of view and theory, but we are very far away from anything that is worth talking about.
Thank you.
So, Dr. Sen, I have a question. I have actually multiple questions. Uh, Maybe I'll give other people the chance to ask, because then I do not want to block all the question pipeline. Anybody has a question? Okay, if not, then I'll ask one thing. Is first of all, as I said, it's a beautiful talk. Uh, I mean, I'm a mechanical engineer, had no background in chemistry, but I love when chemistry is being applied into these applied fields. Um, it's amazing. When you are moving these titanium oxide particles, so you
Yes.
mentioned that it's just a light source. Maybe I have missed that part. So aren't you using some kind of a like a charge-based transport, or is just because titanium oxides are activated by light, so it creates that transport of charges, and that drives the flow? Is that the background?
So basically, the answer is all of the above. So um, the titanium dioxide is a photocatalyst,
Mm-hmm.
and therefore, when you shine light on it, it generates oxygen, for example,
Mm-hmm.
and by splitting water,
Mm-hmm.
and that oxygen causes non-electrolyte diffusive phoresis.
Okay.
Also, light causes local heating,
Uh-huh.
which causes buoyancy-driven flows.
Okay.
And so these two things combine, for example, um, and in depending on the time scale, one dominates over the other. And this is
Mm.
actually a good example where if we did these experiments in microgravity, we
Yeah.
would eliminate one of them, which is the buoyancy-driven flow, and then you can study the other one in much more detail. And so it involves using several different mechanisms, some of which are diffusive phoretic, some of which are buoyancy driven, and so on.
So, but then you just kind of touched upon that. But when you go in a microgravity environment, this
Yeah,
temperature difference can cause surface tension driven flow, right? Which is Marangoni type of a situation, and that
yeah,
might actually, which you are not seeing on Earth, but that might be a completely different mechanism what you will start seeing, right?
yeah. So this is why we're interested in maybe exploring some of these things in that kind of a microgravity situation. Other phenomena, as you pointed out, can emerge,
Yeah,
and
like a
certain
small
phenomena
range.
can be could be suppressed. Yes.
I mean, like a small range molecular forces which are being suppressed by gravity, all of those can come up
Yeah.
and you might
Yeah.
see a very different thing. So I guess, so that brings the question about that equation that you were showing, which
Yeah.
has the diffusive term and electrophoretic terms and all of those things. I think in microgravity, that equation will be then changed, uh, maybe not because of the lack of gravity sedimenting things down, but maybe because, again, I'm just thinking out loud. I may be wrong. Maybe because of the emergence of other forces, which we generally neglect on Earth.
Yes, and for example, if the particles don't settle down and therefore they're not near the wall, then you can completely neglect the diffusio osmotic flow that happens at the double layer of the wall, which
Mhm.
also causes transport.
Okay. Okay.
So that's another one. I
Yeah,
see
because
that there's a
what I
raised
was
hand.
trying to get to is like when you, I think it's at the very early on when you showed the velocity equation,
Yeah,
there is no gravity term because at that scale you
correct,
neglect the
correct,
inertia effect.
correct. Yeah, correct.
But in reality, you definitely have some inertia effect. Uh, so
That
I think
depends on the Reynolds number.
correct,
Reynolds number. Yeah,
correct.
yeah,
Whether you are in the creeping flow regime or not, and those type of thing.
sure.
Um, so I guess so what I was thinking is like there are these forces which are electrophoretic forces and the other things, but maybe there will be your surface tension forces. But I think that will be very interesting, scientifically speaking. Um, so I have more questions, but let me hand it over to Padita. Padita, you have a question. Go ahead, please.
Uh, Thanks. Okay. Your second question about surface tension driven effect. It has been seen, and then that's part of it, I guess. Okay, but it could be both working together. Preferentially, is that see the surface tension driven convection is due to a kind of like a photoisomerization, what sorry,
Isomerization.
photoisomerization. Okay,
Yeah, yeah,
that that gives you a change in the density gradient that push it. Okay, and then you can see these particles moving away. Okay, it has been done a few, well, about 15 years ago, I think, that I was working with them in that isomerization process, uh, that have the what you call it like a uh, photo induced directional um, change. And then what happened was that there was a proof that, as it moves, and while it is moving, it crystallizes. As it crystallizes, what happened? The cis and tra, they change, right? Yeah. As it changed from cis and tra, is that the crystal get bigger as it grows, and all of a sudden, a lot of them sink. So there is a gravitational term involved in it. Okay. So the question is like, I agree to what Suman was telling about, that wouldn't there be a competing process? Thanks.
Well, maybe I missed the question. So in our systems, which is of course on Earth, the surface tension effect is really not very relevant.
Correct. Yeah, it won't be because your
Yeah,
gravity will basically die down.
yeah. But the main thing about gravity is it introduces all kinds of wall effects.
Correct.
And you can talk about surface tension, you can talk about electroosmotic flow, you can talk about settling, you can talk about gravitaxis, all kinds of wall effects, which can be eliminated. And that allows a much better understanding of the different ways active matters can move, interact, and so on. And once you understand them, then you can put the whole thing back together on Earth and say, I want to use this force and I don't want to use that force. And how do I do that? And so on. I hope that answers the question.
No, no, absolutely. I mean, it does. Um,
So the wall effect is it from the what you the molecular or the ion structure itself
all right.
Yeah,
that
so
you're
so for
talking about?
example, the electrodiffusive, the diffusive osmotic effect has to do with the fact that you're generating an ion gradient, and of course you have a charged double layer,
Mm,
and so the flow along the double layer depends on the both the magnitude and the direction of the gradient, and so the flow could be one way or the other way. Um, and so I showed you, for example, attractive predator-prey behavior, and then I showed you this repulsive, what I call the shark chasing a school of fish behavior. So
So Dr. Sen, you were talking about like the double layer or the
yeah,
bilayer type situation. Uh, but how does that affect? Because those things are roughly of the order of what, 10 to 15 nanometer in thickness. I mean, is that causing any challenge? I mean,
well,
that should not affect your particles because your particles are pretty big, right?
there they can be, well, it depends on how much electrolyte you have, what the dimension of the double layer is. Less electrolyte you have, the bigger is the double layer. But
Mm-hmm.
but it's but the flows are significant.
Okay.
The flows can be many microns per second.
Okay. Understood.
We see that. And just to give you an idea on a totally different topic, if you have and if you just take a salt, sodium chloride, for example, and on one side you have zero concentration, on the other side you have say 5 molar, 10 molar concentration, you
Mhm.
can measure the difference in potential, and it's
Yeah.
several volts per centimeter.
Right. Absolutely. No, I understand that. So basically, those layer are basically causing the fluid to flow,
Yeah,
and the wall effect that you were talking about is coming basically from um, shear stress that is generated at the wall. I mean,
yeah,
they have a molecular origin, but from a mechanical engineering
yeah,
perspective, there's just a shear stress
yeah,
that it feels.
yeah.
And I presume all of these were done in aqueous environment, right?
Yes, it's just pure water, deionized water.
Okay, okay. And do you see that if you change the fluid to like a viscoelastic fluid, like a polymers, things will change? And is there?
We haven't, to be honest, we haven't done too much with it. Um,
Mhm.
we've changed the electrolyte concentration, and it behaves the way you expect. You can speed up the whole process. I showed everything in pure water, but if you can speed up the process if you use an organic molecule that can be photooxidized by titanium dioxide. That speeds up many of these processes. But to just keep it simple, I just talked about water. Yeah.
Understand, understand. Any question from the audience?
I see Arlene Velev. Hi, Arlene.
If you're talking or
Hi, I mean, it's a pleasure to hear this talk, and I really enjoyed it. Thank you very
Yeah,
much.
I haven't seen or talked to you in a while, so I just wanted to say
Yeah.
hi.
Thanks. I appreciate that, and I mean that's really such a core.
Yeah.
so apart from Dr. Sen, if I ask you like apart from just fundamental study,
Yeah.
how do you think this can help NASA with their like future missions? Is there anything that you would like to futurescape?
Um, I well, well, NASA. First of all, NASA is into fundamentals, right? They
Yes, yes,
spend
yes,
so much
yes.
money on origin of life, which is as fundamental as it gets. But the the question is that in any kind of mission, you need transport.
Mm-hmm,
Transport, transport, not in a macro scale, obviously, but in the smaller scales, you need transport. You need transport chemicals. You need transport of all kinds of things
mm-hmm,
from one point to another point. Even if you think about fuel cells
mm-hmm,
that NASA uses on spacecrafts.
mm-hmm.
You need transport of protons through membranes, for example, in fuel cells for them to operate optimally. And so the question is, how do you manipulate transport in micro environments in space missions? Everything from, as I said, fuel cells to delivery. And if you're looking at, for example, things like biological experiments, you need to transport nutrients to these samples, and how do you do that, and so on. And so I think this is an important thing. As you know, we wrote this little white paper,
Yeah.
and there's also another paper in I referenced it in my first slide by Volpe and co-workers from Europe on microgravity research. So there are a number of applications that can come out of all this. But I tend to think more about transport, both transport small things, but larger things, swarming, all of which will be useful, I think, in a space situation. But we need to understand that, as I said, the different ways you can do it.
Absolutely. But you see, I when I saw that picture of this thing is basically eating, so it almost looked like phagocytosis, like it's a model phagocytosis system
Yeah,
in biology side.
yeah,
So
yeah,
so
yeah.
but it's very interesting and nice, I should say.
So this force generation in biology
Mm-hmm.
is an important topic,
Correct.
and force generation in biology, we worked some on it, but but again, how does gravity play into that? And different kind of surfaces, cells move differently. Stiffer surfaces, cells move faster than on softer surfaces, and there have been mechanical effects that happen, which are tied to chemical effects like enzymatic reactions and so on. Yeah. So anyway,
No, absolutely. No, absolutely.
yeah.
So Arlen has a question. Arlen?
Actually, I think somebody was raising hands before me, but I mean, okay, let me ask my question. I'm sorry for if I'm cutting in line here, but something that came to mind just because you're discussing now is, from what I have heard, the potential problem with, let's say, extraterrestrial environments is that you have dust that is being kind of like, I mean, actually penetrating everywhere. So can one design the opposite of the type of processes that Usman was showing? Basically get the particles out and keep them there by active means of propulsion out of certain areas where you don't want the particles to come in the liquid phase.
Oh yes, yes, yeah. That's actually a good, interesting points that you can move particles in, but you can also move particles out.
Right.
Yes, yeah, absolutely right.
No, that's a great idea. Padita, is that a hand from before or it's a new one? If you're talking, we cannot hear you. You're muted.
Are you asking me?
Yeah, yeah.
What is it? But I
So
missed it.
is this a old or new hand? So you,
Say it again. I missed it.
so do you have a question?
No, I'm just listening. Okay, sorry.
Okay, okay. Um, no, I think this was really great. And if is there any more questions from the audience?
And you can always, of course, email me, and if you have any questions that crop up later.
Yeah, I'm going to email you. That's for sure. I have a lot of questions that I would like to talk with you more in detail. I
Sure.
it
Happy to.
I have more questions than before, I would say. Positive questions, like things, scientific questions. So
Okay.
yeah, so if there is no other questions, so thank you everyone. Again, I would like to remind that there is another talk coming on 27th of this month, which is on rheology, given by Simon Rogers. And if you want to give a talk, please email me, or there's a form that you can fill out. I think the easiest thing will be just to email me. I will coordinate with you on the topics. So thank you everyone, and thank you, Dr. Sen. Thanks a lot.
Thank you,
Really,
Shubha.
really appreciate it.
Thank you.
And so with that, I say
Okay.
bye.
Thank you.
Great, very fundamental stuff.
Thank you.